Topics of this episode is isotopes and atomic masses. But before that, let's do a quick practice. Last time, we learned one way to represent an element, which is called complete elemental symbol, which is written in this way. X is the symbol, A is the mass number, which is the number of protons plus the number of neutrons. Z is called atomic number, which is the number of protons. Of course, for an atom, the number of protons equals the number of electrons. All right, so let's practice. The first one, fluorine. How many protons? Well, atomic number tells you the number of protons. So this one has 9 protons. Of course, 9 electrons. Protons equals electrons. Neutrons, neutron will equal the mass number minus the number of protons, 10 neutrons. This atom has 10 neutrons. If you understand the first one, you can do the second one, and you're going to find out this one has 9 protons, 9 electrons, and neutron is also 9. 18 minus 9 equals 9. Now what we see here is we have 2 atoms. They are both fluorine. They're both fluorine because they have the same number of protons. Number of protons is the ID of the atom. So they're both fluorine. However, they're different clearly. Their difference comes from the number of neutrons. The first one has 10. The second one has 9. We call atoms with the same number of protons but different number of neutrons. We call them isotopes. So the example, the practice we just did is an example of 2 fluorine isotopes. Isotopes have almost identical chemical property. Again, the chemistry of an atom is decided by its electrons. Remember, electrons are troublemaker. Physical properties of isotopes are often different because they have different masses. Now, how to distinguish them? Okay, how do we distinguish isotopes? In this case, the first one, we can call it fluorine 19. Okay, we use mass number to tell the difference between isotopes. The second one is fluorine 18. In nature, almost all elements exist by mixture of isotopes. For example, we see an example here, fluorine has fluorine 18, fluorine 19. Oxygen has oxygen 18, oxygen 17, oxygen 16, oxygen 15, and more. There are a couple more. So oxygen has quite a few isotopes. Look at a couple more examples. The first one, sodium. Okay, we have sodium 23, sodium 24. Both of them have 11 protons. Since their mass numbers are different, which means they have different number of neutrons. The first one has 12 neutrons. The second one has 13 neutrons. So sodium 23, sodium 24 are 2 isotopes of sodium. The case of hydrogen, the first element, the element that has only 1 proton, hydrogen has only 1 proton. Hydrogen has 3 common isotopes. The first one is called hydrogen. The second one is called deuterium. The third one is tritium. All right, so the mass number of the hydrogen is 1. We also know hydrogen has only 1 proton. If the mass number is 1, that tells you the number of neutrons is 0. The first isotope of hydrogen, which is called hydrogen, has no neutron in its nucleus. In its nucleus, there's only 1 proton. Deuterium, 1 proton, neutron, 2 minus 1, 1. So in the nucleus of deuterium, it has 1 proton and 1 neutron. This one has 1 proton and 2 neutrons. Now we're moving on to atomic masses. Again, however, before that, a couple more facts about isotopes. We know elements occur in nature as mixtures of isotopes. Okay? What we don't know is that isotopes of an element exist in nature at different abundance. What does that mean? Abundance is the percentage of an isotope of an element. For example, for carbon, we have carbon 12 or carbon 13. In nature, about close to 99% of carbon are actually carbon 12, close to 1% is carbon 13. So the 99%, 1% are the abundances of carbon 12 and carbon 13 in nature. Oh, here we go. More accurate numbers. So carbon is 98.89%. There's carbon 13, 1.11%. There's carbon 14. The abundance is very low. The amount of carbon 14 is very small. Those are abundances. Okay. Now we're going to talk about atomic mass. Knowing that we have different isotopes of each element, and isotopes, they have different number of neutrons, which means they have different masses. Now, which mass do we use? Which isotope do we use to represent the mass of an atom? Do we use carbon 12? Do we use carbon 13 to represent the atomic mass of carbon? Well, this is how we do it. We do not use either one of them. We use the average mass for the isotopes. Makes sense. However, this average is not a simple average. It's called calculated weighted average. What does that mean? Well, we're going to talk about that later. But overall, the concept is you cannot take one individual isotope to represent the mass of an element. You have to make sure you average all the atoms of all the isotopes. However, there's a second part of this statement. The mass of each isotope, you're not using purely the mass itself. You're actually using the mass expressed on a scale where carbon 12 serves as a reference point. What is that talking about? Once again, two things we want to talk about in this statement. The first one is the calculated average. The calculated average or weighted average. Well, to be honest, that is not very hard to understand. We're going to talk about that later. Let's focus on the second part. What is a carbon 12 reference? Okay, this is the statement about carbon 12 reference. The mass of carbon 12 is defined to be exactly 12 atomic mass units. Atomic mass unit is called AMU. Then the masses of all other atoms are determined relative to that of carbon 12. To be honest, if this is the first time I'm reading this, I have no idea what this one is talking about. So let's discuss this a little further. Okay, so keep in mind we're trying to calculate the atomic mass of something. Needless to say, the mass of one atom is extremely small. Okay, for example, carbon-12, the true mass of carbon-12 is actually 1.99 times 10 to the power of 10 to the power of negative 23 gram. It is in the level of 10 to the power of a negative 20 something. We all understand it is not going to be very easy to operate on a number like that. If you have to do some addition, subtraction, or other operations on a number like that, it is not very convenient. So chemists were trying to make their lives a little bit easier, simpler. So this is what they did. They said, okay, if we don't like a number like that, then let's try to use different numbers. I don't care what is the true mass of carbon-12. I'm going to define a new mass unit, which is called atomic mass unit. Whatever mass of carbon-12 is, I will say carbon-12 has 12 atomic mass units. Okay? Which means 12 atomic mass units is actually 1.99 times 10 to the negative 23 gram. But you can ignore that. Regardless of what it is, I just call it 12 AMU. Then all other atoms, you know your own mass, use your mass, compare with the mass of carbon-12, get your own AMU number. For example, carbon-13, I don't even know exactly what the mass of carbon-13 is, but I do know if you compare the mass of carbon-13 with the mass of carbon-12, which is 1.99 times 10 to the power negative 23, if you compare that, and if carbon-12 is 12 AMU, carbon-13 is actually going to be 13.0034 AMU. The atomic mass of another isotope, let's say oxygen-16. Oxygen-16 is an isotope of oxygen. If you use the atomic mass, the mass of oxygen-16 atom compared with the mass of carbon-12, and if carbon-12 is 12 AMU, then oxygen-16 will be 15.9949 AMU. Now when you see different atoms looking at their atomic mass, instead of a number that is 10 to the power of negative 20 something, now it is a number like this, which is a lot easier to handle. Okay, that is carbon-12 reference. So all atoms will compare with carbon-12, get your own AMU number. There's a reason why carbon-12 is chosen, and there's a reason why it is assigned as 12 AMU, but we're not going to go into that details here. Weighted average, what is that? Well, weighted average tells you when you try to get a value, the average of certain values, not only you have to consider the value, but you have to also consider how many atoms are at that value. What does that mean? Let's use a different situation as an analogy to talk about it. Let's say I want to get the average of one exam grade of our class. Okay, let's assume in this one specific exam, all the students get only one of the two grades. Students either get 100 or get a 0. And if I ask you, what is the average of that exam? Some of you may want to say, oh, that's easy. 100 plus 0 divided by 2, 50. The average of that exam is 50 points. Well, very likely that is not right, because although there are only two kinds of grades students got for that exam, however, 99% of students got 100 degree points. Only 1% got 0. When you calculate the average, not only you have to consider these two values, the points students get, also you need to consider the number of students get each grade. So what do? You use 99% multiplied by 100. You also use 1% multiplied by 0. You add them together. That will be the average of that exam, which is actually 99, far from the 50 you thought. The 99 is called weighted average. When you calculate the weighted average, not only you have to consider the values that you have to average, but also you need to consider how many atoms are in that value. Make sense? Let's come back to the concept of atomic mass. So how to calculate the atomic mass of an element? How do we do that average? Here we go. You multiply the relative mass of each isotope. The relative mass is those AMUs you get by comparing them with carbon-12. You multiply that mass by its abundance. You do that for each isotope for the element, then you add them together. If this statement is still not very clear to you, let's look at one example. Let's try to look at how to do the atomic mass for carbon. We know carbon, we have carbon-12, we have carbon-13. Carbon-12 have 12 AMU, that's the definition. Okay, it is arbitrarily set as 12 AMU. Carbon-13 is 13.0034 AMU. You have to use the relative mass of each isotope, multiply it by its abundance. The abundance of carbon-12, whatever it is, I don't remember. The abundance of carbon-13, whatever it is, I don't remember. You have to do this. Once you do this, you add this product and this product together. Oh, the abundance of carbon-12 is actually 98.890%. The abundance of carbon-13 is actually 1.110%. Remember, the percentage sign here means divided by 100. So you have to use 98.890 divided by 100, multiply it by 12. 1.110 divided by 100, multiply it by 13.0034. Then you add them together, you totaling the products. Okay, divided by 100, the abundance number becomes 0.9889. The next one becomes 0.01110. You multiply the two, the mass and abundance, the mass and abundance, and then you add them together. 12.01 AMU, the atomic mass. The mass of one carbon atom is 12.01 AMU. An exercise. Chlorine has two isotopes, chlorine-35, chlorine-37. The relative mass of chlorine-35 is that AMU. The abundance is given. The relative mass of chlorine-37 is given. Abundance is given. What is the atomic mass of chlorine? All right. If you know how to do it, pause the video here. Try to do it. You can come back to check your answer later. If you need more hint, keep watching the video. Here is the hint. Okay? With this hint, if you know how to do it, pause the video again. Try to do it, come back for the answer key. This is the answer key.